Payment ME Design Fiscal Year 26 webinar number 4 on PMED traffic module overview and special loading simulations. I'm Hari Nair, the chair of the Payment ME Task Force, and I will be your moderator for today's presentation. Today's presenter will be John Donahue of Applied Research Associates. This presentation is being recorded and will be available on the Payment ME website. Again, I am the chair of the Payment ME Task Force, and Ian Risch of Georgia DOT is the vice chair. The other members include Ryan Fragapane, Astoware Product Director, Ben Said, Astoware Associate Product Manager, Nusrat Morshed with the New Jersey DOT, Kumar Dave with Indiana DOT, Delche Feldman with California DOT, Jason Simmons, Utah DOT, Robert Studler, Maryland DOT, Diana Podboroshinsky, Canadian TAC Liaison, Tom Yu, Federal Highway Liaison. A couple of housekeeping items. We encourage you to ask questions, and those will be addressed at the end of today's webinar. If you have questions, please click on the question and answer button to send your question to the host and the panelist, and we will address those directly after the presentation as time permits. Any questions not answered will be responded to separately.
Oh, I guess, yeah, I'll start out. Sorry. Hi. Going over the prerequisites for this webinar, it's assumed that you've generally had some experience using the Pavement ME Design software, either with the desktop or the web version. Now, I will say, though, that as we go through this presentation, the screenshots will be specifically from the web version, and really it's getting to the point to where I think everyone's going to have to start getting used to that, because we do have a sunset date of the end of next June of 27. So we're about a year away from where we stop actually providing tech support for the, well, not totally completely, but we're really gonna have to wean people off of using the desktop version. So definitely a great time to start getting familiar with the web version if you haven't yet. Okay, learning outcomes. We're going to understand the types of inputs for the PMED traffic module, and I'll apologize ahead of time because I know if you've used the software, you do have some familiarity with this, and so I'm not going to try beating a dead horse to death here, but we will try to maybe go into a little bit of detail about the importance of the different inputs with regards to the analyses. We'll talk a little bit about the chart generation options, which is in there, providing basically different cumulative ESL and truck class totals over the design period. And then we'll talk a little bit, got a couple examples looking at how to configure special axle load scenarios, whether or not it's simply heavy loads, or if they, or could be, and or also having some unusual axle configuration that's outside the norms of the regular single, tandem, tridem, quad axle configurations. So the outline is going to be, we'll get into the inputs, talk about what's actually being done with them in the analysis, talk about the limitations, what you can't do or can't do as well with the traffic module. And then we'll also talk about the special traffic module, which is available in the software. And then give a heavy load configuration example, and then an unusual axle configuration example. Okay, stepping through the traffic inputs. The first tab you see when you're in the traffic module is the one marked AADTT for total truck traffic. And this is pretty self-explanatory. Total number of trucks, number of lanes in the in the design direction, percent trucks in the design direction, which is normally going to be split 50-50, but it doesn't have to be that. Percent trucks in the design lane, which is going to be dependent on the number of lanes in the same direction. And then finally, the operational speed. And this number gives you basically your total number. So if you have your total ADTT, your total number of trucks, and then you basically whittle it down based on the number of lanes, percent trucks in the design direction and in the design lane. The next tab is traffic capacity, and for most people, this is going to be the least important feature here as far as traffic goes. And it's simply putting a limit on the number of trucks that are physically able at a certain operating speed to exist within a lane within, I think, on an hourly basis. And that these limits are derived from the highway capacity manual. Seldom something you have to worry about. You'd have to be in a really, really congested situation in an urban area. In almost, I'd say, 99+% of situations, though, it's not something you'd have to worry about. Axle configuration. This is providing the physical spacing characteristics. The axle width itself, which is going from outside of the wheel to outside of the wheel on the other side of the axle. And then the tandem, tridem, and quad axle spacings. That's the distance from wheel center to wheel center of each axle within. So in other words, a tandem axle, it's the spacing between those two axles. Tridem axle, it's the spacing between the three axles. Dual tire spacing. Now, pavement MED design in the analysis, the assumption is that the tires are dual. So you cannot model, well, there's an exception with the special traffic module, you can, but with the regular traffic module, you cannot model like a super single or single tire situation. So the assumption is your wheel is actually two wheels, and then you're going to have spacing between those wheels on each side of the axle. And of course, tire pressure is meant to be the hot tire pressure, so it's not necessarily when you first inflate a tire. It's after it's been running on the road for a while, it's going to heat up and increase in pressure. And that's basically the hot pressure. So, oh yeah, and I mentioned too that some of these inputs are only used for the rigid design because they're important with relation to the position of the axle or the wheel with the geometry of the concrete slab, how close it is to the edge, how close it's going to be to the transverse joint. So it's not actually used in the flexible or the semi-rigid pavement analysis. And then the next tab, lateral wander, and this is providing whatever the design length width is. The mean wheel location is the wheel edge of wheel location from outside edge of wheel to the outside edge of lane, and then the standard deviation or wander of the vehicle. And again, we have a couple inputs here that are only relevant for the concrete pavement designs, not for the flexible or semi-rigid designs. And just visually kind of showing you what we mean by traffic wander here. So, and these numbers were derived from a lot of national data. So this is basically national averages. So the mean wheel location, again, is from the edge of outside of the wheel to the outside edge of the pavement. And the average has been 18 inches. And then the wander is the standard deviation of the wheel location. And that nationally has been 10 inches. Next tab is wheelbase. And this is the space for defining it as short, medium, and long axles. is the space from basically one set of axles to the next set. So it could be the center of a single axle to a tandem axle, or the center of a tandem axle to the next tandem axle. That's basically what the definition of the axle of the spacing for axles is. And then for each of those three categories, then you're going to assign a percent of that number. And of course, the three together should total 100. And this also is only used for rigid design because this affects basically the center slab stresses, either top down or bottom up, or damage that manifests in transverse cracking. As far as where is one axle in relation to a joint versus the rear or the front axle in relation to the next joint. And just to visually kind of explain what we're talking about here, you can see wheelbase being the distance between different sets of axles. And actually, it's not to the center of the tandem axle, it's actually to the center of the first tire in the tandem axle. And then axle spacing is going to be the distance from one tire to another within the same axle configuration. And also, too, is in terms of the spatially for the analysis, the direction of traffic is going to be considered the y-axis. And so these measurements are along that axis in the direction of travel. Whereas the axle width is going to be the distance from outside wheel to outside wheel, which on average, as we mentioned, is about 8.5 feet. And then the dual tire spacing is from center to center of the each set of tires on one side of an axle. And that's going to be, for analysis sake, that's going to be considered along the x-axis. And they'll kind of explain that a little better later. The vehicle class distribution is how the 10 different vehicle classes are broken out. You have the distribution percentage, which the total of all 10 should, of course, add up to 100. You're inputting what the growth rate per year is, and then whether that growth function is going to be linear or compound. And this kind of shows you visually what each class is. The first three are light traffic, and so they're not used in the design analysis because they really don't provide any. Or the loads are light enough to where they're insignificant as far as accumulated damage goes. And the next 7 you can kind of divide into, I'm sorry, not 7, but 1, 2, 3, 8. Yeah, 8. Or 9. Wait. No, sorry, 10. Yeah, 10. That's right. Yeah. You can divide into 4 classes, or kind of 4 groupings. One by itself would be buses. The next category would be the single unit trucks with, single unit trucks with 2 sets of axles. Now, they could be a tandem axle, could be a tridem axle, but it's only going to be a tridem plus a single, or a tandem plus a single. And then the next 3 categories, 8 through 10, are going to be your single trailer units where you've got a tractor pulling. You have an articulated vehicle and a tractor pulling a trailer. And then the last three categories, 11 through 13, are going to be trucks with multiple trailers. Now, there are default categories. This was derived from the Wayne Motion scales that were at the LTPP sites set up around the country. And based on those, there are 17 groupings that were developed. And they're broken out by percentages of different classes of trucks. and this would be considered a level 3 input. Ideally, you'd like to collect your own data within a state and either do some type of clustering, grouping of that data, or even using project-specific, site-specific data. But these are always a good backup. The monthly adjustment factor is for each class of vehicle, you're going to have a percentage of them on a monthly basis. Here, the default values you're seeing are just once. In other words, each truck classification is spread evenly among all 12 months, and your total should be 12 for each class. Axles per truck, for each vehicle class, you're going to have an average number of single, tandem, tridem, quad axles. That again is information that there's default values within Pavement MED Design, but it'd be good to collect your own data from state WIM sites. And axle distribution. And so this is for each class vehicle, for each axle type, for each vehicle class, you're going to have a bin distribution. For single axles, they range from 3,000 up to 41,000, I believe. And you're going to have a percentage of your total number of axles within one of those bin categories. Again, the total should be 100%. So you do this for each month, for each vehicle class, for each axle type. It's a lot of data. There are default values for this as well. There's the one that was derived from the original 137A study, but then also there have been 4 groupings using LTPP data, a heavy, a light, or typical, or kind of average, and a light default values, and then a global default, which is essentially an average of the other 3. And so, lacking your own information, you can use one of these as level 3 inputs. Hourly adjustment is the percent trucks on an hourly basis throughout the day. And this also pertains only to the rigid design. It's important because of the changes in slab curvature over the course of a day, from curling and warping, from changes in temperature and moisture, and the loading, or the percent of trucks loaded on the slab at a particular time during the day when it's has a certain curvature, is going to factor into the fatigue damage for that. It's not to say this is irrelevant for asphalt or flexible or semi-rigid design, because it is, because obviously as the temperature changes throughout the day, that's going to impact the dynamic modulus, and therefore impact the prediction models as well. But it's not used for right now. It's only used for the rigid design. Okay, now the traffic charts. There's some relatively simple accumulations of truck growth that you can generate for yourself if you want to see it. One is the total number of trucks in the design lane at different periods during the design period. That's cumulative heavy trucks. The next one is total truck growth by class group. So remember, I mentioned that the 10 truck classifications can kind of be split into 4 categories. You've got the buses, single unit trucks, tractor trailer, and then multi-trailer combinations. And then the next chart is each class individually. You can see that growth over the design period. Total trucks by class. So this is the total number of trucks, bar chart showing the total number of each of the 10 classifications over the course of the design period. And then finally, you can generate what the cumulative ESOLs are going to be at the end of the design period. So Nothing too complicated, but people are general, and these don't really pertain, or they're not directly important to the analysis itself. But a lot of people, especially ESOLs, like to see, have a comfort level with seeing those parameters. So that's why they're here. Now, looking at this another way, we can kind of split these into kind of roughly three different categories as far as where this information is coming from. So some of this is basically specific to the roadway. Um, you're going to have a certain amount of truck traffic in different corridors and a growth rate. And then also based on the number of lanes and um, based on the reasons for generating traffic, uh, that'll dictate what the percent of trucks in the design direction is, and then finally operational speed. So, and then there are the categories of inputs that can be derived from the weighing motion data, axle load distributions, their configuration, the normalized truck volume distributions, monthly adjustment factors, hourly distribution factors, and then the third category, which is going to be particular primarily to the trucks themselves, like spacing, tire pressure, and then typically what the lateral wander is of trucks and the different wheelbase lengths. Yet another way of looking at this too is how is this information used in PMED? So, with the average annual daily truck traffic, and then also some of the other variables, you're able to total the number of axles in the design lane. And then by knowing what the distributions are, and then the seasonal and hourly factors, and the axle weight distributions, you're able to generate the critical mechanistic response calculations. Lateral variation is, of course, important for the concrete designs as far as how often the trucks are to the edge of pavement, and also too for asphalt as well, because whether or not the loads are going to be concentrated within a narrow band, which is obviously going to increase the number of repetitions and have an effect definitely on plastic deformation. And then axle configuration, which this pertains strictly to the concrete analysis as far as where the wheels are in relation to either the edge of the slab or the joint. And traffic capacity, which I said really isn't of any significance unless you're designing in a very high traffic urban corridor. Okay, so the analysis engine for using this data is the Julia program, which is the linear elastic analysis program and embedded within PMED design. So the analysis is always going to be along basically the center of, several points. And these points are fixed. So along the x-axis, which is, again, lateral across the roadway width, the assumption is that the wheels are always going to be the wheels, which, again, would be one half of an axle, are going to be centered over around the y-axis. And your spacing is generally, default is going to be 12 inches. So the center of each tire is going to be roughly 6 inches from the y-axis. It's not really drawn a scale there, as we mentioned. And then you've got your average tire load, for in the case of an 18 kip axle, is going to be 4,500 per tire because you have 4 tires on a single axle. And tire pressure default's usually going to be around 120 psi. Based on the tire pressure, the program will calculate what the contact area and the tire radius is. So that's going to be derivative of whatever the tire load and the pressure is on there. Those locations along the x-axis, those are the points of analysis, and those are fixed. They are fixed based on what the tire spacing is and the tire contact radius. In the y direction, the analysis points are also going to be fixed, but these are going to be based on the spacing from one set of wheels to the next set of wheels within either a tandem or a triadem or quad. And the triadem and quad axle spacing are combined. So the spacing, the y-axis locations for triadem and quad are going to be the same for both. And just to show you, this is the table showing what the actual X locations are going to be. And this is based on the default values of 4,500 pounds, 120 PSI, and then with the tire spacing of 12 inches. So these numbers are fixed. You cannot adjust those. This is where the analysis is going to be performed. So X and Y are constant, and apologize that last bullet got cut off there, but what I meant to say was for structural response, only one location is going to be used, which is going to be the critical location. Obviously, where you have the highest, stress strain response is going to be where your maximum damage accumulation or strain hardening is going to occur. So that's and the predictions are going to be based on that one location. Okay, so let's talk a little bit. What are the limitations of running the traffic analysis? I mentioned earlier, you cannot model or place a super single or wide base single tire within the traffic mix. The assumption is always going to be that's a dual tire, except if you use the special traffic module, and you can actually have a single tire for that. Can't simulate non-uniform contact pressure. So if we're saying the pressure is 120 psi, we mean every square inch is going to be 120 psi. Of course, in reality, you do have nonlinearity in tire pressure depending on the location within the footprint area. But for analysis purposes here, we're assuming it's even. No hourly distribution of truck traffic for flexible and semi-rigid or hourly, the HDF table that showed you. And so you can't differentiate changes in modulus between day and night. And also, too, is a couple points related to construction staging. So you're not going to be modeling or incorporating the impact of having heavy equipment during construction on different layers. Similarly, if you do stage construction where, say you place an 8-inch pavement, plan on putting 2 inches 10 years later, you can't really, well, there might be a way of doing it, but it's kind of messy, but there's not a nice clean way, let's put it that way, of simulating that in pavement MED design. So you're sticking with one design thickness through the analysis. Okay, now getting into some special axle weight configuration situations. You have a choice. So if you have something out of the ordinary, in other words, you don't have a nice simple single axle where you have 2 tires on each side, or tandem axle where you have 2 consecutive axles with 2 tires on either side or for each one, and they're not of normal axle width or distance between the tires. Something that, and if it's a heavy load too, if it's going beyond what the what the maximum bins are in the PMED design, you have a choice. So you might be able to come up with a workaround with the regular traffic module, and there's ways of doing that. Or you could use the special traffic module. So the special traffic module. Now, where is it? Okay, one, it's only available for new flexible designs. You can't use it for concrete, can't use it for semi-rigid, can't even use it for an asphalt overlay on an asphalt pavement, and that's primarily because the stress intensity factors for reflection cracking in this situation have not been worked out for the special traffic module. So it's got to be new flexible design. And then for that, you will see at the bottom of that screenshot, use special traffic, click that box, and then when you go to the traffic module, you're going to see the input screen for that, and that's what this looks like. So here we go. We've got the tire locations, so you can enter up to 10 different tire locations. You have a maximum number of 10 tires you can model in the special traffic module. You are limited spatially to plus or minus 48 inches in each direction. So plus 48 to minus 48 along the x-axis, plus 48 to minus 48 along the y-axis, which gives you a 8 by 8 foot square. So that's what you have to play in when you're locating tires. And then as far as the analysis goes, you can only analyze or pick locations along the y-axis. You can't go laterally like like the regular Julia analysis for the regular traffic module does do that. It has the fixed locations laterally and longitudinally. In this case here, you're just picking location. Obviously, one location is going to be 0, which is usually going to be your critical location. But if you have some weird configuration to where possibly the critical or the maximum mechanistic response may be somewhere further along longitudinally, between a set of different axles, you can check at those points. But for this, you also have a maximum number of 10. So if you exceed 10, enter more than 10, you're going to get an error message. You won't be able to run the analysis. Okay, and just to kind of show you visually what's happening here, you see on the right side, you've got your X and Y axis, you've got plus or minus 48 inches in both directions. And again, it should have had that showing it for the Y axis as well, but it's minus 48 to plus 48 inches for both X and Y. And here it's showing 8 tires. So you've got like one axle with 4 tires across, and then you have 2 adjacent axles with 2 tires each. The x-axis, sorry about it. I apologize. I had this wrong. You cannot input different x-axis locations, but there are actually analysis points along the x-axis, but they're fixed. And it's basically 13 different points. It's every 8 inches. And you can see that, usually you're going to try to center center it evenly around the y-axis. And it's just a matter of figuring out how you can place these so that you get as many tires as you can, up to 10 tires within that 8 foot by 8 foot pad to work in. Now, it's really important to be able to know what every set of tires is, how it's impacting another set of tires. It all comes down to the amount of stress that's superimposed at any one location. So, and this is very, very simplistic, but this is just showing you where you have three sets of tires of dual tires. They're close enough such that the center tire, the subgrade below there, is going to have stress influence from the set of tires on either side. And then as you bring them further apart, you can see each adjacent set of tires uh, creates a point to where their influence is superposed in a location, and then when they're far enough apart, they really don't matter. And of course, this is just basically influencing the unbound layers. The tires would really have to be tight, almost on top of each other, in order to superpose the stresses that are induced under one set of tires. And you can run the analysis. Just you can kind of do a sensitivity analysis and see how tire spacing matters, and you'll see that really until one dual tire is really close to another, or a single tire. Again, you can do single tires with the special traffic module, but until they're really close to each other, they're not really going to have a cumulative effect within the bound layer itself. It's going to be more in the, usually typically the unbound granular layer, or stabilized subgrade, or deeper into the subgrade, is when the strain accumulation is going to be compounded by that. Now, limitations of the special traffic module. Again, it can only be selected for the new flexible design. You can't combine distresses with regular traffic module predictions. So, in other words, you can't just combine, you can't run this for a special piece of equipment and then run the design for all the other traffic you have during that analysis period, and then just add them together for distresses. Definitely doesn't work for rutting because you're using a strain hardy concept, so it's not cumulative. Now, for cracking, you could accumulate damage if you want to look at because we're using Miner's hypothesis for combining damage increments. I suppose you could run it and then run the regular model and then take those, but you can't combine directly the cracking that it's going to induce. You can't do that. But again, that's going to take some extra effort to do something like that. So just as a rule of thumb, though, you can't directly combine distresses between the special traffic model and the regular traffic module. The load has to be the same for all tires. In some cases, it doesn't really matter because you're assuming that. But in other cases, you may have one axle that's far more heavily loaded than, say, a rear axle. And we'll kind of look at an example of that soon. In that situation there, you got to stick with one or the other. And, obviously you're concerned about, but I was saying that the load has to be the same for all tires. And a lot of situations doesn't matter, but other situations it might, because one may be much more heavily loaded than the adjacent axle. And so you have to make a decision about what's more important to look at. And then the tire pressure has to be the same. So again, your load's got to be the same, and the tire pressure also has to be the same for each tire. The 10 tire limit, already mentioned that. And, realistically, within an 8-foot by 8-foot analysis pad to work with, it's going to be kind of tough to fit more than that in there anyway. Again, the lateral and also longitudinal analysis limit of 8 feet. Okay, now, not a lot of people use this, And so there's been discussions at the task force meetings about probably discontinuing this, perhaps looking at improving the existing traffic models so that we don't have to use a special traffic module. So there's, a couple different directions this may go in the future. So if you have any strong opinions about this, I would let someone in the task force know this, or maybe contact somebody in AshtaWare or even ARA is fine. Whatever, however you want to make that known. But if you strongly, if you're passionate about the special traffic module, it would be good to hear that, because we really don't have a lot of feedback on it. And honestly, I think right now the general opinion is leaning towards discontinuing it. So anyway, just food for thought there. Okay, so let's go look at a couple examples here. So this is a heavy load example. In this case, we've got a forklift loading containers, two single axles. The front is loaded. You're going to have 40,000 pounds. The rear axle is going to be 15. As far as the number of passes, 50 passes per day loaded. Dual tires on the single front axle, and then single tires on the single rear axle. Again, if we're using payment and design, you are just using the regular traffic module, it's going to assume that rear axle has dual tires. It can't, it's not going to model it with a single tire unless you use the special traffic module. We're going to assume a little longer spacing of, well, no, it's not really, 12 spacing. Actually, 12 foot's not that long, really. 12-foot spacing between axles. Axle width is a little wider than usual. The average, again, we mentioned was 8.5 feet, and this is going to be 10 feet. And then the spacing between the front dual tires is 12 inches. So in this case, we're going to use the regular traffic module because our maximum axle load, our maximum single axle load, is still within the inference space of the bin categories used in payment ME design. Because I mentioned before, the maximum axle weight is 41,000. So, and here we're using 40,000. If we went with heavier loading, we'd probably have to use the special traffic module. And as far as what the structure is, in this case, we're going to assume we've got 10 inches of asphalt on a 6-inch crushed stone base on a clay subgrade. So looking at the special traffic module input screen here, again, we mentioned 50 passes per day. So that's going to be our two-way AADTT. And to force all of the passes in one direction in one lane, we've got one lane. We're going to say 100% trucks in the design direction, 100% trucks in the design, or 100% trucks in the design lane. Operational speed, we're going to say 20. There is a limit of 15. So, a lot of situations it's probably slower than 20 miles per hour, but you can't go below 15. So you'd have to limit it at that. I'm sorry, I said special traffic module. This is not the special traffic module screen. This is the regular traffic module screen. Yes. Okay. So going through each of the tabs. And then the axle configuration. Average axle width is 10 feet from outside tire to outside tire. And then the dual tire spacing is 12 inches. We're not concerned about tandem, tridem, or quad axle spacing because we don't have any with the forklift. And then the tire pressure, we're going to assume 120 psi for that. The traffic water, we're going to assume is tighter than 10 inches. 10 inches is, appropriate for trucks on a highway at 60, 70 miles an hour. A slow-moving operation here, generally within a confined area, 6 inches is probably reasonable standard deviation. In fact, it could even be a little lower than that probably, but we're going with 6 inches. We're all of our axles are going to have the same spacing. So it's 12 feet. And so we're going to make this the short axle category, and we're going to assume, 12 feet and 100% of that, and then zero out the medium and long axle categories. Okay, now as far as what are we going to liken a forklift to? In this case, we're going to liken it to a bus, a class 4 vehicle. Single axle in front, one in back. And, potentially we could have made it a class 5 vehicle, but we're going to say class 4. So all of our vehicles are this. So we're going to put 100% of it in class 4, and I'm going to assume a growth rate of 1%, linear growth. And then we have to zero everything else out, and our total is now 100%. For monthly adjustment factors, we're going to assume it's evenly distributed, so we don't have to change what's currently there. Axles per truck, all we care about is the class 4 category. We have 2 single axles, no tandem, so we've adjusted those. And then axle distribution, we're putting all our eggs in 2 baskets. Half of the axles are going to be at 15,000 pounds, and the other half are going to be at 40,000 pounds. And so, here again, all we have to do is change the single axle category for class 4. Unfortunately, we have to go through every bin for every month. And I did the math on that. It's, I don't know, around 350 or so screens, going from 3,000 pounds per bin to 41,000 pounds. This is just showing you part of the screen. So this is just showing you 3,000 through 10,000, but it's in increments of 1,000. So you can imagine how many of these you have to go in and manually change. Here's an idea too. If you think this is a good idea, I do, since I had to go through doing this recently. Maybe it'd be nice to have a feature where you can zero everything out, because if you're doing some type of special truck configuration, it's all going to be the same of one type, and you're just going to have a couple weight bin categories to fill out a percentage on, but everything else is going to be zero. So it might be nice to be able to zero everything out and then go ahead and place, in this case, I put 50% for each month for 15,000 and also for 40,000. But this does take time to go through and do each one singly. So might be some room for improvement there. And, please, again, let the task force know if you think that's a good idea. Okay, and this is just showing you what the results were. 50 passes per day for 10 years doesn't really add up to a lot. Total rutting was 0.28 inches, asphalt 0.13 inches. Fatigue damage was relatively minimal, so nothing unusual there. The thermal cracking, unrelated to loading, really. It's a factor of the creep compliance and indirect tensile strength, so it's mix related. So obviously you can improve that by just using a better surface mix. We used just a default mix for this. All right, now the second example is, what if we have a really weird looking vehicle that's transporting some type of oversized tank or something, windmill turbines, whatever. This is an actual vehicle. In this case here, the trailer has 18 axles. Each axle actually has 8 wheels across. And so you look at this and you got to decide, okay, what are we going to use? Well, first of all, the load on each axle is 65,000 pounds, over 65,000 pounds. and the maximum bin limit for single axle in pavement ME design is 41,000. So you're way out of the infra space for the loadings that were, you know, I mean, those the weight loadings in pavement ME design were derived from real life data. That was the range of single axles. Tandem axles go up to 82,000, and I think Tridem and quads go up to I think 102,000. So any way you compile these or aggregate these axles, you're still going to be way over what's available within the bin. So obviously for a single axle, 65,000 is way over 41,000. If you want to combine two axles together and call it a tandem axle, that'd be 130,000 pounds. That's way over 82,000 pounds. And then if you want to call it a tridem axle, you're up at what, 195,000? And you know, the maximum tridem axle and quad axle is 102,000. So any way you slice it, you've got heavy loads that are kind of beyond the analysis range of the regular traffic model. So in this case, we're going to go with the special traffic module. The other situation here too is to figure out, okay, how are we going to configure these wheels on in the special traffic module. So looking at the weights here, and I kind of rounded down in this case. You can see I'm calling the axle at 64,000 for each one. 8 tires per axle, so we have a total of 144 tires. The load per tire is going to be a nice even 8,000 pounds. Spacing between axles 56 inches. Spacing between the dual tires is 25 inches. Now we have 8 tires across, but we're going to say each set of 2 tires, you know, within those 8 tires is going to have 25-inch spacing. Tire pressure is actually a little lower here. It's 115, and truck speed is 10 miles per hour. That's another thing I forgot to mention about the special traffic module is that you're not entering the operating speed. So there's an assumed speed that probably translates, I think it's 10 hertz. So that'd be, I don't know, 50, 60 miles an hour, way faster than what you're actually modeling here. But you know, it is what it is. That's what you're stuck with. Okay, and for the pavement that this is going on, we're going to assume, I mentioned already, we're using the special traffic module, 1 trip per month, and all the other traffic is light such that it's inconsequential. So all that really matters is going to be this vehicle passing over the pavement once per month. And as I said before, it's not like you could go ahead and run the other traffic model, the regular traffic model for any other traffic and add it together because you can't aggregate the distresses together. So in this case here, 6 inches total of asphalt on a 5-inch egg base on a A6 soil. And here we are seeing the special traffic module input screen. So our monthly repetitions, 18. Yeah, this is wrong. It should be 8,000. But anyway, close enough. Tire pressure is 115. Now, tire placement. Okay, so ideally, you would like to, you know, get maybe at least one tire right on the y-axis. And kind of maybe maximize the response that you're going to get at that point. The problem here is we have 25-inch spacing. So 4 tires, or I'm sorry, 5 tires spaced at 25 inches would be total of about what, 100 inches? Yeah. Or 4 tires. Oh, wait, okay. So the issue here is you can't neatly put a tire at minus 48, one at minus 24, one at 0, one at plus 24, and one at 48. In other words, you can't fit 5 tires on there with 24-inch spacing because the spacing is 25 inches. So the next best thing to do here, and there is an error in this that I just noticed, sorry about that. So you can put one at minus 48, put one at minus 23, and then the next one should be 2 inches. You go to 2 inches, and then the next wheel would be at 20, should be 27 inches. Sorry about that. The placement of those wheels is wrong. So what you're doing is you're getting one wheel kind of as close as possible to the y-axis and maintaining 4 wheels within the analysis area. If we wanted to have a tire directly in the y-axis, we'd be forced to only have 3 tires because we could have minus 25 inches, 0, plus 25 inches. The other outside wheels would be beyond 48 inches, so we wouldn't be able to fit it. So it's basically making the best of a mediocre situation here. Figure, okay, let's get as many tires as we can and get one of those tires as close to the y-axis as possible. So that's why those, and again, those last 2 locations are wrong. They should be the 2 inches and plus 27 inches. Okay, the standard deviation, we're going to assume 0. We're going to assume that it's smack dab in the middle. It's going slow enough. They're very focused on driving in a straight line with something like this, and so it's not wandering all over the place. All right, and this just shows you what the results were. Again, only 1 pass per month. 18 passes. Okay, another thing I forgot to mention. We're calling it 18 passes, even though it's only 1 vehicle pass per month, but we have 18 axles, so we're calling each one of those axles a repetition. Now, I just want to go back here quickly and look at this device again, and let's, if we were to use the regular traffic model, and let's say that the maximum loads were more reasonable. Let's say each single axle load was actually 41,000. So there's a bin for that. So we can apply that within the regular traffic model. We have 18 total single axles. So we could call that 18 single axles. We could call it 9 tandem axles, or 6 tridem axles. Doesn't work out for quads. So you can play around and combine those axles together, and then input that number of axles into the analysis. Perhaps do a sensitivity to see how it affects the outcome. I guess if you're going to take anything away from this, is that there's not a clean, neat way of doing it to maybe everyone's satisfaction. You got to use a little bit of creativity. If it's really a heavy load, you are stuck using the special traffic module. But again, that's again outside the inference space of the actual loadings that were measured, through the LTPP program. So, whether or not the damage accumulation is going to be the same at those, or the model is going to apply to the damage levels that high, it might be a little questionable, but you're making the best of the situation. I'm trying to think if there's something else I want to go over on this, but basically, I think that's about it. So I have no idea how many questions there are, but I'm going to turn this back over to Hari, I think, or Ben, or I'm sorry, not Ben's not here, Ryan.
I launched the poll. We're at time, so I appreciate everyone's time today. I think Hari probably has some final words, and then before you leave, please take the poll.
John, I don't see any questions in the chat box.
Good in there, though. Working.
That sounds impossible.
No, there were no questions in the chat box, so if people have
Okay.
questions after, they can reach out to ASHTO or to ARA directly, and we'll get them answered. And I know there was a question about if this would be recorded. Yes, it's recorded, and probably early next week it'll be available on the YouTube channel. We'll send an email with a link to everybody.
Okay. So one of two possibilities: either I answered everything, the more likely situation, I made a mess of something here and they don't know what to ask. But anyway, all right.
Thank you for joining us today, and we hope you found the information provided helpful. Just a reminder that the recording and the slides for this webinar will be available on the PMED website, as well as you can find all the previous webinars also in the website. Please feel to reach out to any of the contact listed in this slide for information about ASHTO PMED design. Thank you.